Hello everyone, welcome back. Welcome back to the Technology Innovation Hub. Now we have done two sessions on generic career development. So right away let's start the third session. Right. So let me share the screen. We discussed the third video. That is what we finished. Let me put full screen. Yeah, these things we have already discussed, these points. And the last video of this, the baby's brain, the secret life of the brain. So that was the last video. And I may remember the examples that they were given in the video, right? So one of them were the phone call example. I may remember in the network, right? Let's say if you just try to get a real world example like phone network. So when you make a call, it goes to the network, serves the particular location where the number that you want to be dialed, then it rings. That's how it goes. So if you map the same scenario to the brain also kind of a neural network. The particular location or the particular action is like kind of a phone call, right? So because if that particular phone call you are using regularly in day-to-day life, it will be in your memory, right? Likewise, but in a neural network within the brain, if a certain experience or if a certain activity is being carried out regularly, so that is getting sharpened network, that then circuit will get sharpened and it will continue. That's what they are trying to say there with that example. And if a certain particular experience action is not going to repetitively used so much of times and it is very rarely used, that means it's like to discontinue. So this is what the Blooming circuit and the Cronin circuit, that's what they were explaining there using the phone call example. So while the most essential phone call rings, the other calls also rings, but not quite frequently as the major call, right? I mean, the particular call, particular experience is always taking place so that that particular circuit getting sharpened. The other circuits are not so sharpened. So that is what the example that they are trying to explain in the video using the phone call. Okay. So let's go to the next one. Next in line, we have the development milestones, right? So let's go there. In that, this is from CBC, right? Let's check that. Yeah. The CDC development milestone. So this one is gives the mental development, cognitive development as milestones. You can see 2 months, 4 months, right, 6 months. And if you click 6 months, you can see the important milestone. Your baby is 6 months, or these activities, right? You have social, emotional, language communication, cognitive, moments likewise. And the nicer thing is this is in text form here, but if you go back, let's say I'm going back, if you go down a little bit, you can see view milestone in action, photo and video gallery. Right? See here, the spelling is in pictorial and visual form, right? So you can see here milestone in action. So let's say I want to take 1 year, and not only the photos, you have the video library, right? Is shy or nervous with strangers, cries when mom or dad leaves, having has favorite things, specific attention on certain toys, has favorite people. So likewise, so just take a look at those videos, and I mean you can get an idea about your child or the career up to 1 year now, because you can see whether is he growing with the time in parallel or is any development is lacking. So you can get the complete understanding from there, because it's very important, because you are just putting the foundation for a future better career. I mean, the whole goal is to have a better brain architecture which supports the future career goals. So that is what, right? Okay, let me go back, and again, we have another PDF as well. Just take a look at it. This is a little bit comprehensive guide, and yeah, it will give you everything at all in one. So let's check that, right? PDF. So yes, your baby at 2 months. So that is because I have selected 2 months. So it gives a PDF for 2 months. Just take a look at those things. It will be very important for you. Let's continue to our next one. So next one we have early brain development overview. Yes, early brain development overview. So this is another video, right? Let's take a look at it. Yeah. All right. So this is the YouTube channel which presents that video, right? From this Kendra Gagnon, right? That's fine. And so let's listen to this. Let me play that for you. Yeah. So early brain development overview. That is the video next year. So let me play that. Let's listen carefully. Right?
In this video, we're going to briefly review development of the central nervous system in the embryo, fetus, and young child. And you'll see here that I've started with a drawing, a very rudimentary drawing of the brain. And so we're going to start by talking about the embryo. And so when we talk about the embryo, we're referring to the first 8 weeks after conception. And in the first 18 to 28 days after conception, the neural tube forms. And the neural tube is what really gives rise to the entire central nervous system. So once the neural tube closes, the central nervous system begins to develop in sort of a bottom-up direction. And so the first thing that begins to form after the neural tube closes is the spinal cord. So I've colored the spinal cord in blue here. And so in the embryo, we can see that the spinal cord begins to form, and not only is it formed, but there actually starts to become some connections between nerve cells in the spinal cord, which then produce movements. So we can actually see movements in the embryo well before the mother can feel those movements. The brain begins to develop during this time, and by the end of the first trimester, the brain is formed in a very primitive sense, with it being roughly divided into a forebrain, midbrain, and hindbrain. Now, as we move on to the fetal stage of development, we see that the brainstem develops and begins to function. So in the second trimester in pregnancy, months 3, 4, and 5, we start to see brainstem function. And so we know that the brainstem actually controls sort of reflexive movements. So what we start to see is our breathing movements in the fetus. So of course the fetus isn't breathing in there, but we're seeing kind of rhythmical contractions of the chest wall and the diaphragm that look like breathing. We also see some suck and swallow reflexes. And from a kind of a cellular perspective, in the second trimester, we're starting to see neurons or nerve cells begin to form, proliferate, and migrate. So they start to form and differentiate and start to migrate to the different areas of the brain where they'll eventually live. By the end of the second trimester and into the third trimester, we start to see some formation of the cerebral cortex and some development of the cerebral cortex. And that's indicated in my drawing here in green. And so the first parts of the cerebral cortex that really start to develop are the primary motor and sensory areas that are just beginning to function at birth. And by birth, we do see that some synapses are beginning to form as well. And when we talk about synapses, we're talking about connections between the different nerve cells. And so that's really beginning to happen in the third trimester and then really starts to accelerate once the baby's born. So what do we see in terms of brain development at and after birth? Well, at birth, the brain weighs is really quite large, and that's why babies have a larger head relative to their bodies, but it still only weighs about a quarter of the adult brain, a quarter of the amount the adult brain weighs. And so the brain still has a lot of developing left to do. Neurons are largely formed by birth, but they're very poorly connected. So synapses or connections between nerve cells have begun to form, but they haven't started to form in a major way yet until birth. And so what we see is that after birth, we see this huge burst of synapse formation that occurs where babies are experiencing up to millions and millions of connections per second that will result in a total of trillions of connections. And so this begins this what we call a stage of blooming and pruning. And so the blooming phase really starts immediately after birth and occurs in the first few years of life, and into early childhood, where the brain actually produces more synapses than it's ever going to need. And so this overproduction of synapses begins earlier in sensory regions. So this is why babies have better sensory function than they do motor function for a while, but then eventually goes on to motor and higher areas of the brain that control things like judgment and emotion and memory. So through early childhood, you see this huge burst of synapse formation. And then by middle childhood, you see sort of a pruning effect where it really is kind of a use it or lose it. There's that huge overproduction of synapses that allows for lots of learning and plasticity, and for the baby and the child to learn from a variety of experiences. But if those synapses or those brain connections aren't used, they die off and they go away. And that's considered to be the pruning stage of development, and really allows the brain to function a lot more quickly and more efficiently in the adult. So at the same time that this blooming and pruning sort of phenomenon is occurring, we're also seeing myelination occur. And myelin is this fatty substance that covers the nerves. And so if you think about, like an electrical wire that has the kind of the plastic coating on it, that coating is there to allow that electrical signal to travel quickly and efficiently down that wire. And that's how myelin works on our nerves. And so myelin is this fatty substance, it covers the nerves, and it leads to faster and more efficient transmission. And so similar to synapse formation, myelination begins earlier in sensory regions. So again, that's why we see more sophisticated sensory functions in children, and then eventually progresses to higher areas, including motor areas and areas of the brain that control things like perception, judgment, and feelings. And so this myelination actually occurs through even the early 20s. And so that's why we see even teenagers and individuals in their early 20s don't always show maybe the best judgment, is because those areas of the brains are still truly not developed yet. And so this occurs, blooming and pruning and myelination occurs from childhood and even into early adulthood. And while the blooming and pruning phase of development is really very much dependent on sensory experiences to determine which synapses are truly kept, myelination is really thought to be more hardwired and is really not influenced much by the environment at all. The only specific environmental influence that's been identified is nutrition. And again, because that myelin's made up of fat, children that don't get enough fat in their diet tend to have some issues with neurological development because of that poor myelination. So that, in a nutshell, is a summary of central nervous system development from the embryo through birth and even into childhood and early adulthood.
All right, so that is that. And if we just recap certain points in that video. For example, you can think about now, here it says after birth, right? After birth, the blooming stage, the rapid development of synapses. So the connections happens before 3 years, right? So second year, third year, very fast pace, right? So some may think that that may be the reason why these preschool teachers try to give a lot of things for the kids. Right? They try to teach everything in that age. Right? But I don't think that's the correct approach to do. Anyway, so that is the time this rapid circuit development happening in a very fast way, just before 3 years, right? So after that, the selection will happen depending on the experience, the input, the learning. Selected things will continue. That is known as blooming. Others will get pruned. That means those circuits will get discontinued. So anyway, let's take a look at those things more detail later as well in our career development explanations. The other one is this myelination process, right? So that is also very important. And it is said that it's happened in childhood and adulthood. And in terms of age, right, it can go till 20, right? Even beyond 20, early 25 age, 25 years of age. And okay, we can see some examples now. Let's say now teenagers are very aggressive, but they are lacking in decision making, right? They hesitating to make decisions. They need assistance on critical matters. So as per the explanation, one of the reasons is their myelination process is not completed yet. They need the attention of adults when it comes to critical decision making. And that may be another reason why some of those, I'm not teenagers, the university students like beyond 18 years, some of them are very like to protest. Protest means on the road, demanding certain things, right? That's maybe they can't make the correct decision, right? So like that. But then again, not only those people, even the adults beyond 30s, right? They're also trying to come into the road and do protests. Right? In certain countries, these things are very common, even in these days. These days, this is on a pandemic situation, right? The primary requirement is to stay safe, keep the 1 meter distance. But some of these, even the adults, right, the matured, known as matured in terms of age, right? They are on the road protesting. But again, there are a set of people who are known to be intelligent and decent who does not want to. Even in the entire career of their life, they are not on the road in terms of protesting against something. But they nicely balance their life and continue it. I mean, they know how to get the well-disciplined, well-decent, intelligent, educated personality. They know how to maintain the educated, intelligent, well-disciplined, and personality. So that is another category is there in society. So we need to understand this difference. What is the difference, right? Certain people are, on the road protesting, but others are not. This is just one example I'm just telling. Right? Even in a critical era, critical time period like this, can be explained through this myelination up to a certain level, because it's all about your decision making happens according to the neural network that is in the brain, right? Okay, finally, that is the ultimate mentality. Okay, anyway, so that affects the career as well, right? So a lot of things to discuss there, but let's talk about later little by little. So up next what's going to be, let's think this one now. We were here, early brain development overview. The next one is, how does child's brain develop in detail form? So these are just explained little by little in milestone likewise. Right? Certain videos explains the early, right, prenatal and just after birth, and certain videos came up to third year. And this video, last one, of course, with the myelination, it went up to even 20 years of the explanation of certain things with the brain development. But this video is a thorough video, comprehensive video, right? It's explaining right from the beginning to the adulthood. But this is a little bit lengthy, so I'm not going to play it the whole thing, but I'll give you the initial part just for you to give an idea what this going to look like. Let me just click here.
Hello, welcome to
Yeah, so this is from How Does a Child Brain Develop? Dr. Susan, so Bukhema, and so it's from this YouTube channel, use UCLA Health, right? So just listen to it carefully, and once the slides are uploaded, you can click there and get the full video. Let me play it, the initial stuff at the moment. Let's just listen carefully what she's trying to tell. All right, let me play it.
Hello, welcome to today's UCLA Health webinar. My name is Dr. Susan Buchheimer. I am a professor of psychiatry and biobehavioral sciences here at UCLA, and I do research in brain imaging. Today's topic is going to be, how does a child's brain develop? During this talk, you can ask questions on Twitter at UCLA MD Chat, or go ahead and just ask a question on Facebook. We'll save them for the end. Today, what I'm going to be focusing on are, first, how brain development is designed to form connections, which together we call the human connectome. I'll also talk about how these connections relate to brain function. And I'll talk about the adolescent brain, the teen brain, and why that teen brain is so, let's say, difficult. I'll also talk about a few things that can go wrong in brain development because of these abnormal connections that can develop. And then I'll mention some studies that were going on at UCLA now that you could consider participating in. One of the first things that we need to know about brain development is that it's really not about size. The brain, in fact, does get bigger, but that's not really what's important. What's important is what's happening inside. Brain development is all about forming connections. We are actually born with a lot more brain cells than we're going to use. And in two critical periods of development, at about age 2 and then again at adolescence, we actually lose a lot of neurons. During this period of time, however, our brains are forming connections. The good ones, the ones that we are using, are going to be maintained, and the rest are going to be pruned away, just like we would cut off an old branch that is no longer useful. So we use the phrase, use it or lose it, when we think about brain development. In this way, there's a very important relationship between our environment and our brains. What our brains are exposed to, what we do, what we see and experience will all help determine which of those connections are going to stay and which ones are going to be cut away. This is a picture of the fetal brain growth from the age of 25 days all the way up to birth. And you can see that the brain starts very, very primitive and very quickly develops into having the general brain shape. But the main thing that changes is the folds in the brain. The folds in the brain, which give rise to this characteristic brain pattern, are there because they increase the surface area. By having folds, we can get more neurons into that tissue. And the more neurons we have, the more we are able to use that information to do complex tasks that humans do. So humans have the most folded brains that there are. There are 3 major changes that take place during brain development. The first one is what we call the proliferation of dendritic branches. Just as a tree grows with a long central stalk, which we would call in the brain an axon, it also develops all of these branches. And brain cells sprout these branches, which connect to other brain cells. So that's one thing that occurs. Another one is this process called myelination, which I'll show some pictures of in just a bit. But this is a covering of the axons. These are the major branches that I was talking about. And this myelin is made of a very fatty substance that actually comes from a certain kind of neuron. And it's like an insulation material that allows information to process and to be sent very quickly from one brain cell to the next. And finally, there's that process of pruning, dying off of brain cells and brain connections that look as if they're no longer needed. Here's a picture of what it looks like across development. In the newborn brain, we have a fair number of neurons here, but as you can see, they're very simple. They've got a single long axon that's not really connected to anything, and only a few little branches, and the cells themselves are quite small. During development, these branches really start growing quite a bit, although the actual number of neurons is not changing. By 9 months, you can start to see many of these connections forming and becoming more complex. But look at the age of 2 years. Look how incredibly dense all those connections are. They're the same number of neurons here, but that's connected, everything is practically connected to everything else. However, if you contrast that with the young adult brain, you can see that a lot of those connections have started to prune away, and the cells themselves are larger, And the connections between cells are thicker. They've become stronger with age, but there are fewer of them. This is the general process where we talk about a transition between brain plasticity, that is the potential for the brain to do a lot of different things, and brain efficiency, that is just keeping those connections that we need so that we can use our brain energy as efficiently as possible. This is an MRI scan of a 7-year-old and a 30-year-old to demonstrate one of these processes, and that is the thinning of the gray matter, the pruning or the breaking away and dying off of neurons. In the young brain, the 7-year-old brain, you can see that there's a lot of this thick gray matter around here, and you compare that to the same area in the adult brain where it looks much thinner. So between the ages of 7 and 30, we are still losing a lot of neurons. This graph actually shows the statistical change over time from the age of 5 through the age of 20. The brighter colors mean thicker cortex, the darker colors mean thinner cortex. And so the brain thins, although different areas of the brain thin at different rates over this period of time. And in fact, the frontal lobes are the last areas of the brain to thin. They don't even complete their maturation until at least the mid to late 20s. Now I'm going to talk a little bit about myelination. These are brain scans from the age of 1 week through the age of 10 years. And of course, you can see that the brain has gotten a lot bigger. But one of the other changes that you can see pretty clearly here is that this brain looks very dark, as does this one, whereas these brains look much lighter. Well, the reason why that's happening is because we have no myelin, none of that fatty substance in the infant brain. It slowly starts to develop and then accelerates incredibly rapidly. So it's the myelin that makes this white matter, these connection tissues, look very, very white. And I'll explain a little bit more about myelin and how that works. This is a picture of a brain cell called a neuron. And this is the axon, that long central branch that will lead this brain cell to another brain cell in order to make connections. At birth, there is no insulation around any of these connections. But what happens is a certain kind of brain cell comes in and forms a little sheath and wraps itself around that axon, and a number of these different neurons wrap themselves around the axon. It's like the kind of insulation that you would see on an electrical wire. We don't actually see the wires, we just see the plastic surroundings. That insulates the wire. It allows that electricity to move safely within that wire. But here in this case of myelin, it also allows something special to happen. Since the brain communicates with electrical signals, this fatty substance allows those signals to skip over from these different nodes all the way down. It allows sort of a speed diamond pathway of connection. And so the more myelin there is, the faster these connections can form, and therefore the better the communication can be between two different brain regions. In this MRI scan that we see here, we are seeing the infant brain from the first 100 days of life up into 300 days of life. So this is early in the first year of life. This is the MRI scan, and this area down below just shows that white matter, the part of the white matter where the myelin is, that fatty substance that helps form those connections. At birth, almost nothing is myelinated. In fact, there are really only two areas of the brain that have this myelin that allow for this rapid connection. One is the visual cortex, so eyes through the central part of the brain into the visual system. And the other is the mouth motor cortex. And you can guess why. An infant doesn't have to do very much except find what it wants to suck and have the motor system to suck it. That's all an infant wants to do. But as the infant starts to develop, more and more systems come online. This myelin starts to get formed, and it allows the child to develop faster and better cognitive skills. So the more that brain is in use, the more that this white matter starts to develop. And we see that within 1 year of life, we go from almost no myelin to a well-myelinated brain. This is another picture of this, comparing again that same 7-year-old with a 30-year-old. And I've just outlined here the white matter of the brain, and you can see this is the white matter, this is where the neurons are, and these are where the connections are. And you can see how much that white matter has grown over that period of time. So where the gray matter has shrunk, the white matter, the connections, have grown. So it's all about forming connections. Here's another picture of connections that you might have heard about. This connection is called the corpus callosum. It's a connection of those fibers, those connecting fibers between neurons that connects the left side of the brain to the right side of the brain. And this is a picture of the brain cut right down the middle. So this would be the nose, this is the back of the brain, the top of the brain, and this is right down the center here. You can see in the 7-year-old, here is the corpus callosum here in white, and you can see how thin it is right here and in the back. Whereas at the 30-year-old level, it's very nice and thick. So over time, our two hemispheres have learned how to talk to one another and to do it very, very quickly and efficiently. So why do we have all of this connection? Well, different parts of the brain have different roles. Each part of the brain does something different, but it doesn't do it all by itself. To work, every part of the brain has to talk to other parts of the brain. It sends electrical signals throughout the brain through those white matter tracks to form these connections so that different areas can talk to each other and work together to perform complex tasks like talking, as I am doing with you today. And this is all about connectivity, or what we would call functional connectivity. That is not just the structure of those pathways, but what those pathways are doing and the cognitive skills that can emerge because the brain is using those pathways to talk to other areas of the brain.
All right, so very informative, I'm thinking, right? So I think it's very useful. Just watch the complete video. So, I mean, it's around 40 minutes, right? Okay, so I think with that, we can, in our presentation, let's check it. Yeah, so that's going to end our first slide, the explanation. So, principles of early neural development. So the next in line, we have skills for successful journey. The skills for a successful journey. So let's talk about that in more detail in the next session. So I'm going to stop here. So I'll meet you soon. Have a great time. Bye-bye.